Okay. Now students, we will go for a new discussion, that is significant figures. In that same chapter, this is a portion that is the significant figure. So, what is significant figure? First we will know that, then we will go for rules for the significant figure, how to calculate the significant figures in a measurement. So, the significant figure comes, as we know that any measurement is not absolutely correct. Any measurement is not absolutely correct. Means what? Any measurement is not absolutely correct means what? Now take an example. If we measure a length and we express the length as 14.5 centimeter. We measure a length and we express 14.5 centimeter. And another person comes and he measured and he expressed the length as 14.52 centimeter. Then another person comes and he measured and he expressed that as 14.527 centimeter. What this means? It means when you see these measurements, it shows that if you see these measurements, clear? So, in these three measurements, here when you see this measurement, you can say that the first portion, the first one, used a device. The device has a least count of 0.1 centimeter. Means the device can measure the minimum distance of 0.1 centimeter. That is the least count. In the second observation, this is the least count. In the second observation, we can say that the least count of that device he used is 0.01 centimeter. Means obviously this is not the same device. Then the third observation, the least count is 0.001 centimeter. It means for different instruments, the measurements are different, and according to that, for different devices, the measurement is different. Means here he used a device where the least count is 0.1 centimeter. He used this, second person used this measurement, the second one used this, express this measurement with least count 0.01 cm. That device has a least count of 0.01 cm. For the third one, this is the measurement, but the least count is 0.001 cm. Clear? So, from here what you got the information that for different devices, the same measurement gives you different values. For the same measurement, same length measurement and the same physical quantity, that is length, but by using different instruments, different devices, the measurement is different. Clear? So, from there we got an information that here we can say that in the measurement, in this one, these are, 1 is significant, 4 is significant, but this one is not significant. But this one is not significant. Means it is not certain. It is not certain. Means it may change. 5 may changes to 6, or 5 may changes to 7, or 5 may changes to 4, like that. So that is uncertain. Similarly, in the second one, this 1 is certain, 4 is certain, 5 is certain, but 2 is not certain. The last digit is not certain. In the third observation, 1 is certain, 4 is certain, 5 is certain, 2 is certain, but the 7 is not certain. So it is uncertain. So this gives you the definition of significant figures. Okay. So now you write the definition of significant figure. Now what I will write here, what is the significant figure means? The significant figure is that significant figure are, let me write this definition, significant figure are the significant figures are those digits in a number in which the digits with certainty and a digit with uncertainty. What it means? The digits with certainty and a digit with uncertainty. What I told you in the example, that in that measurements I have given the example there. I told that some of the digits are certain, but when I go for the last one, that is uncertain. Means the certain digits are certain, means in that measurement the digits will come, these values are there, but the last one may change. And that is, the change is based on the using of the device, using of a measuring device. According to different devices, the last digit will give you different values. Okay. So now we go for another example. Suppose I measure a length. Okay. So if this is the length I want to measure. So what we are generally do for measuring this length? We use a meter scale or the scale what is available in your compass. Okay. So use a scale, put the scale here, and the zero of the scale coincide with one of the end, then the last end, the other end of this coincide with that number, which gives you the length of this line. So suppose it coincided the length, that is suppose here it is suppose 9.3. It coincided 9.3. So it is 0, it is 9.3. So when you measure by this meter scale, you will say that the length of this one is 9.3 cm. But this is clear. It means what? There is the division is, suppose here is your 9, this is 9.1, 9.2, this is 9.3, this is 9.4, like that, 9.5, 9.6, like that. These are the divisions. But in this measurement, now you see clearly that if this is coincide at 9.3, 1, 2, 3, at this length, you can say 9.3. If the length is not at 9.3, this end is in between 0.3 and 0.4. The length is in between this region. The point is in between 0.3 and 0.4, means this is the portion where this is 9.3 and 9.4. Then what the length you will see? In this case, one can say it is 9.3 or one can say it is 9.4. It means when you measure and express the value, this 9.3 cm is by you, but that's 9.3. If the length is in between this 0.3 and 0.4, one can say that it is 9.4 cm also. Because you don't know, because there is no division in between 0.3 and 0.4. Why? Because the least count of the scale is 0.1 centimeter. So according to that, to know this significant figure, and after knowing these significant figures, then we will go for the what are the rules to know the significant figures. Now we will go for the rules to calculate the significant figure. Clear? Now we will go for the rules to calculate the significant figures, to know the significant figures of a measurement. The first one is The rule number 1 is all the non-zero digits are significant. All the non-zero digits are significant. What it means? A non-zero digit means maybe 1, 2, 3 up to 9. So in a measurement, if 1 to 9 number is there, then we will calculate that is a significant figure. That is a significant figure. So in this measurement, suppose I will write an example like 12.34. Here, if I will ask you what are the significant figure in this measurement, then in this calculation the number of significant figure is how much? 4, because all are non-zero. Similarly, another I suppose 1.28. What are the significant figure? Here it is 3. 235. What are the significant figure? Here it is 3. So in this way, because all are non-zero, so this is the rule number 1. All the non-zero digits are significant. Clear? Now the next rule is the zeros lie in between two non-zero digits. Zeros lying in between two non-zero digits are significant. Are significant. Now go to the rule number 2. The zeros lie in between two non-zero digits are significant. Suppose you have a measurement, let us take an example, 107. Here this is a 0 which is lying between two non-zero digits. So that's why the significant, here 0 is also significant. But in the rule number 1, it does not tell about what about the 0. In the rule number 1, it does not tell you what about 0, because non-zero digits are significant. But what about 0? What about the 0? That comes in your rule number 2. If a 0 lies between any two non-zero digits are significant. So in this measurement or in this calculation, you can say the significant figure is 3. Suppose you have given 2005. Here you see there are two zeros are in between the non-zero digits. Now according to this rule, these two zeros are also significant. 2 is significant, 5 is significant. These two non-zero digits are also significant. So I will write here as 4. Clear? The significant figure is 4. And suppose similarly, if you say 5, 6, 9, 0, 0, 0, 0, 3, what are the significant figure? All the zeros are significant. Means these are 3 plus 4 plus 1, 8. The significant figure is 8. Clear? So this is the significant figure. And next, rule number 3, the significant figures do not change. The significant figures do not change if we measure a physical quantity. If we measure a physical quantity. If we measure a physical quantity. If we measure a physical quantity in different units. In different units. What it says? The significant figures do not change if we measure a physical quantity in different units. Means if you change the unit, then the significant figure does not change. As you know, we come across the different systems of unit in CGS, MKS, SI, FPS, the systems of unit. If you measure any physical quantity and using a CGS system or an SI system or an FPS system, now if I change the system of unit for measuring the same physical quantity and same quantity, then the significant figure does not change. Example is that like that. Suppose I have 2.5 centimeter in a measurement. So in that case, if I write, what are the significance of this one? This is a 2. If I write the same centimeter, as you know, 2.5 centimeter means one can write 2.5 into 10 to the power minus 2 meter. Both are same thing. 2.5 centimeter is equal to 2.5 into 10 to the minus 2 meter. Here also, in that case, if you see, it means 10 to the power. That does not affect the significant figure on counting the significant figure. While counting the significant figure, 10 to the power, right, that does not change. Means here also we will say that the significant figure is 2. The significant figure is 2. Clear? Then similarly another, if you go for, suppose I have 5 kg. So 5 kg, this can be written as, what is the significant figure? 1. 5. 1 is the significant figure. So if you write that in gram, I can write this as 5 into 10 to the power minus 3 gram. As you know that 1 kg equal to 10 to the power minus 3 gram. So 5 into 10 to the minus 3 gram. So what is the significant figure here? Same one, because here it is a 1. It means that while in measurement and expressing that measurement on basis of significant figure, if you write the 10 the powers of 10, that does not change the significant figures. Okay, is that clear? Now we go for the fourth one. Let me erase this one. Now let's come to the rule number 4. The rule number 4 is that, what this rule number 4 says, that all zeros to the right of the, all zeros to the right of the last non-zero digit, all zeros to the right of the last non-zero digit are not significant, are not significant, are not significant. Is that clear? All zeros to the right of the last non-zero digits, last non-zero digit are not significant. Suppose I say an example like that. Example, take an example like, I have 30 measure value I have written, it is written 30. So now I will ask you, what is the significant figure? Here we will say that 30 all zeros to the right of the last non-zero digit. Means after this there is no digit is followed, there is no non-zero digit, so don't go for that after that. But this is a non-zero digit, last non-zero digit, and this is the zero coming after the last non-zero digit, so this is not significant. Means here the significant figure is 1. Here the significant figure is 1. Similarly, another if you write 300. In this 300, what is the significant figure? So in this case, also we will write the significant figure as 1. Because these zeros are not significant, they are false after the non-zero digit. Suppose in a measurement there is 20060. What is the significant figure? Here while calculating the significant figure, remember, you will use not this rule only, you will use the previous rule also. Here the zeros are coming in between two non-zero digits, so they are significant according to your rule number 2. The zeros lying in between two non-zero digits are significant, but according to this rule number 4, the zeros to the right of the last non-zero digit, according to this one, after this non-zero digit the zero follows. So if the zero follows means this zero is not significant. It means this one is significant, the zeros are significant, and this one is significant. Because according to rule number 2, these are significant, the zeros are, but this zero is not significant, so this is not significant. So the significant figure you will write as 4. This says you rule number 4. Okay, clear? Now we will go for the rule number 5. So what this rule number 5? All zeros to the right of a decimal point. All zeros to the right of a decimal point. To the right of a decimal point. All zeros to the right of a decimal point and to the left of a non-zero digit. And to the left of a non-zero digit. Non-zero digit is not significant. Are not significant. Are not significant. Not significant. Now go for this an example. All zeros to the right of a decimal point means the number has a decimal point, okay, and the zeros to the right of a decimal point and to the left of a non-zero digit are not significant. For example, if you take 0.03, now you understand this rule. All zeros to the right of the decimal point, this zero is to the right of the decimal point, this zero, and to the left of a non-zero digit are not significant. Means you will write here is significant is what? This one only. This is not significant, and obviously this zero is not significant because this is 0.03. So you can write this as this is not significant, and this zero is also not significant. Clear? Then if you go for another example like that, if I write 0.0043, what is the significant figure? Here you see in this expression, in this measurement, 0.0043, this zero is not significant, this zero is not significant, because they comes what? The zeros to the right of the decimal point. These zeros are to the right of the decimal point and to the left of a non-zero digit. So this is not significant and this is also not significant. So which one is significant? These 4 and 3 are significant. So I will write this as the significant figure as 2. Clear? So this is the method to know calculate the significant figure. Now we go for the sixth one. What the sixth one? All zeros to the right of a decimal point. All zeros to the right of a decimal point. To the right of a decimal point. To the right of a decimal point and to the right of a non-zero digit, 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 and to the right of a non-zero digit are significant. Are significant. Are significant. Clear? All zeros to the right of a decimal point and to the right of a non-zero digit are significant. What it means? Example, 0.350. 0.350. So if I will ask you what is the significant figure, now we will use the rule number 6. What this says? All zeros to the right of a decimal point. This zero is to the right of the decimal point. Clear? And to the right of a non-zero digit and also to the right of a non-zero digit are significant. So this here we will write the significant figure is 3. This 0 is significant, but this 0 is not significant. Right? So this is significant. And again I will take another example. That suppose 2.0050. What are the significant figure? Now you see these zeros are, forget about the decimal. First, these zeros are between two non-zero digits. So they are significant. So this is obviously significant and this is significant. The point is, all the discussion is about the zeros. What we will consider the zero as a significant or not. Because according to the rule number 1, all the non-zero digits are significant. Clear? So that is the rule number 1. But for the zeros, we are discussing all these things. So these are significant, but this 0 is according to rule number 6 is after the right of the decimal point and to the right of the decimal point and to the right of the non-zero digits are also significant. Clear? So this means we will write this as how much? 5. But according to the rule number, I think third one also, I think according to the fourth one it is there. But in this case, if it is 300, these are not significant, it is only 1. But in this case, after this decimal point, after this non-zero digit, to the right of the non-zero digit, then it is significant. Clear? So these are the rules to know the significant figure. By using these rules, now you go for the calculating the significant figure. Okay students, don't get confused. If a number is given, then you recall your rules in your mind, then put the rule which is fit for that measurement or that number, then you calculate the significant figure. Okay. Now we will go for the rounding off the measurements. Generally we are rounding off, right? 3.57 round off after decimal, one place after decimal. So we will write 3.657 means we are writing 3.6. That is called round off. Means instead of taking a number of digits after the decimal points, we are just rounding up to make it smaller. So that is the use of this rounding off in the measurements. Okay. Now we will go for the rounding off. Now we go for the rounding of the measurements. So what these rules are there? Again we will go for the rules for rounding of the measurements. The first, already you are familiar with this first and second, but the extra we will discuss here. But the first one is that if the digit to be dropped in a number, if the digit to be dropped in a number, if the digit to be dropped in a number is less than 5, is less than 5, then the preceding digit remains unchanged. Then the preceding digit, then the preceding digit remains unchanged. If the digit to be dropped in a number is less than 5, then the preceding digit remain unchanged. Example is that suppose 7.34. If I go for rounding off, one place after decimal means I have to drop which one? 4. If the digit to be dropped, which one should be dropped? 4 should be dropped, because I will go for one place after decimal. I will round up. In a number is less than 5. So if this 4 is less than 5, so 4 is obviously less than 5, then the preceding digit remains unchanged or it remains unchanged. So I can write this as equal to 7.3 with rounding up. 7.3. Clear about this? Clear? Or suppose example, if we take another example, is 2.981. If I drop the last digit, then what I will do here? Means I will drop this one, means I will take 2 places of decimal. So here I will round up this one, then the drop digit, the digit what is dropped in a number is less than 5. So this is less than 5. 1 is less than 5. So the preceding digit remains unchanged. So I will write this as 2.98. This is the rule number 1. Then we go for the rule number 2. 2. If the digit to be dropped in a number, if the digit to be dropped in a number is greater than 5, then the preceding digit is raised by 1. Do the example like this. Take the same example like that. 7.37, and if I want to drop one place, I want to drop this last digit 7. So if I round up this one, then the last digit to be dropped is greater than, obviously 7 is greater than 5. So if you round up this one, then this should be raised by 1. So I will take this as 7.4. The 3, if the digit to be dropped, this digit is dropped, 7 is dropped, is greater than 5, obviously greater than 5. Then the preceding digit, what is preceding to 7? 3 is raised by 1. So I will write 7.4. That is the method of writing the rule number 2. Then I will go for the rule number 3. Let me erase this one. So the last two rules we have discussed about dropped, the number to be dropped is less than 5 or greater than 5. Now a question arises in your mind that if the digit which is dropped is 5, then what we will do? That is the important thing. Clear? That is the important thing. And these two rules already you are using and already you are familiar with these two rules. Clear? But the third one is that if the digit to be dropped in a number, if the digit to be dropped in a number is 5 or 5 followed by zeros, is dropped 5 or 5 followed by zeros, then the preceding digit remains unchanged. Condition is that remains unchanged if, that is important, if it is even. Got this rule? If the digit to be dropped in a number is 5 or 5 followed by zeros, then the preceding digit remains unchanged if it is even. Let's take an example like 3.65. In a number 3.65. If the digit to be dropped in a number, so generally we are rounding up for this type of, in decimal, after decimals we are rounding up, is 5 or 5 followed by 0. So if I want to drop this 5, okay, then the preceding digit, now if you drop this 5, now you see the preceding digit remains unchanged if it is even. So 6 is a even. What are the even numbers? 2, 4, 6, 8. They are even. Odd is 1, 3, 5, 7, 9. They are odd. So if this is even, then remains unchanged. So if you round up this one, 3.6. Is that clear? 3.6. 13.6. And if the case is like 13.5800, sorry, 5850. If I want to drop this 5. So the rule number, in the same rule, if the digit to be dropped is a number is 5, I want to drop this 5, not this one, 5, or 5 followed by zeros, 5 followed by zeros, or 5 followed by zeros, there is a 0 followed by 0. Then the preceding digit remains unchanged, this preceding digit, so this I can write, the preceding is 8, and 8 is an even number, means the preceding digit remains unchanged. So I will write this as 13.58. 13.58. This is the rule number 3. Then next we will go for the fourth one. I will change here the fourth one. Now we go for the fourth one. I am making the, what are the changes there? I am making the change here the same, no need to write again. If the digit to be dropped in a number is 5 or 5 followed by zeros, then the preceding digit is raised by 1, is raised by 1 if it is odd. If it is odd, this is important. Preceding digit is raised by 1 if it is odd. Means, go for the example is that if I write a number is like 6.75. Now if I want to drop this 5, so if the digit to be dropped is a 5 and there is no zeros are followed, if there is 0, no problem, that 0 is also there, zeros. Then the preceding digit is raised by 1 if it is odd. Now see the preceding one. If 5 comes, then you see the preceding number. So the preceding number is 7, and 7 is an odd number. So you have to make that raised by 1. So I will write this as equal to, if I drop this one, 6.8. Means what? Always if 5 is dropped or 5 followed by zeros is dropped, then see the preceding digit, make the preceding digit as even. According to 3 and 4, make the preceding digit as even. If it is even, keep that as even. If it is odd, make that as an even by raising 1, not lowering 1, raising 1. Okay. So you can raise here, lower means 6.6 also, means 0.6 also, but it should be raised by 1 because you will go forward, we will not go backward. That is the symmetry of nature. Clear? So according to that, another example I will take here. Let 3.7350. Sorry, 3.7350. Now I drop this 5, 0, this number. Then according to this 5 followed by zeros. So if you round up, then see the preceding, it is an odd. So I will write 3.7, make it even, 7.4. Odd means if you add 1, then that is even. Okay. Clear? So these are the rules for rounding up the measurements. Okay. Now we will go for the, already we have discussed our significant figures and rounding up. Now we will go for the rounding or significant figures in the algebraic operations. When we are doing the algebraic operations, what is the role of the significant figure? Means in our measurement, dear students, now you see here, when you are measuring something and you are expressing, that measurement has an uncertainty that gives you significant figures. And if that significant figure is there, and if you are multiplying two quantities or dividing two quantities or adding or subtracting, then in that case the significant figure plays a role. significant figure plays a role, because the significant figure gives you an idea about the certainty of the number, up to what number the quantity or the measurement is certain, because significant figure gives you an idea. So in the result, I will express the result with more certainty. Instead of making less certain, I will make it is a more certain. So significant figure plays a role. So now we will go for the significant figures in algebraic operations. So now you see here the significant figures in algebraic operations. Now in this discussion, so as I have already told that what is the use of this in operations? Operations means algebraic operations, addition, subtraction, multiplication and division. That the four common mathematical operations. In that operations, when you are making the operations, means suppose in the you are adding two or more quantities, or you are subtracting two or more quantities, or you are dividing, or you are multiplying, then in that case what the significant figure plays the role. The thing is that when we add two like quantities, generally two like quantities are added or subtracted. So I will go for the addition and subtraction first. First I will go for the addition and subtraction. And the rule is same for both. So that's why I am writing addition. So that's why I am writing in one for addition or subtraction. Or subtraction. Because the rule is same for both. So I am writing in one addition or subtraction. Okay. Addition or subtraction. Now, when we add two like quantities, then the final result cannot be more accurate than the least precise quantity, quantities. Here, what an example, take an example. Suppose 1.5 meter, 1.5 meter means if it is 1.5 meter, as in significant figure, in the discussion of significant figure, we know that 1.5 meter, right? So this 1.5 meter is having some precision, and again another number, another measurement, another length measurement is 1.53 meter. We are measuring another length 1.53 meter. Now I will add these two. So in this case you see, if you compare these two, 1.5 meter is, which one is less precise? This one. Because it is measured by a scale which has the precision is how much? 0.1 meter. The precision is 0.1 meter. But here it is measured by a device where this is 0.01 meter. More is the numbers after the decimal, that is more precise. Yes, okay. So that is more precise. Already you know about accuracy and precision. That is discussed in the last videos. We have discussed about accuracy and precision. So my point is that out of these two lenses, this 1.5 meter is less precise. That is, it is accurate up to 0.1 meter. It is accurate up to 0.1 meter means it may be 1.6 or 1.7. It may be 1.6 or 1.7, maybe, right? But in this case, it is 1.5 confirm, but this 3 may be 1.52 or 1.54. There is some error factor, 1.52 or 1.54 means you are getting after that another digit you are getting, because it is measured by a device like that, where we can say that accurate up to 0.01 meter. So if you make the summation, addition or subtraction of these numbers, then the point is that then the final result should not be more than the final result should not be more than the least precise number. Means the digits of the final result should not be more than the least precise number. because this is the least precise and this is the more precise. Comparing these two, and the result should be of this form, which is of a least precise, because the result you cannot take up to this precise number, means up to accuracy 0.01 meter. You can take up to accuracy 0.1 meter, right? Because this is the lowest one, so you will consider the lowest one. Okay, let me write this rule so that you can get a clear. So this is true for addition and subtraction. That's why I am writing this. So the sum or difference, the sum or difference of the quantities should have the same number, of digits to the right of the decimal edge the measurement with the smallest number is the measurement with the smallest number of digits to the right of the decimal. Smallest number of digits to the right of the decimal. That is the important point. Clear? This is the point to be remembered. Clear? The sum or difference of the quantities should have the same number of digits, means the result, the sum or difference of number of quantities and the result had the same number of digits to the right of the decimal as the measurement with the smallest decimal number of digits to the right of the decimal, means which is a least precise. Precise means after decimal how many numbers are there, according to that decides the precision. If 1 digit after decimal, least, 2 digits, more, 3 digits, again more, 4 digits, again more. So you will consider the least precise. That is the point. Okay, or you can say that if you are adding the numbers are like that. Clear? Suppose I am adding 2.3 and 2.42. Now you add these two. So what is the addition you will get here? 2, 7, 4. Now you see here. What the result here? After decimal. Now count the decimal numbers. Here it is decimal. After decimal, how many numbers are there? 1. Here it is after decimal 2. In the result, you will get 2. But you will not keep this result. According to this one, the result is that to the right of the decimal is the measurement with the smallest number of digits to the right of the decimal. Which one? This one. How many? 1. So you have to keep 1. Now comes to your round off. So if you write the result here, rounding off. Now go to the rounding up. That is the use of this rounding up. You are dropping which one? After one place means this should be dropped. There are two places means this should be dropped. If you drop this 2, then 2 is less than 5. So the preceding one remain as it is. So you can write 4.7 is the result. 4.7 is the result. So that is the method of addition operation using the significant figures. Means here we are not doing any calculation, you are just counting the number of digits after decimal point, which is the least, that should be in the result. Clear? After decimal. Similarly, you can go for the subtraction. Let me write in the subtraction part. Suppose I get a result like this for subtraction. So let us take subtraction is like that. 9.742 clear minus 6.02. Do the subtraction. 02. What the value we will get here? So obviously we will get 2, then 4 minus 2, that is 2, 7 minus 0, 7, then 3. 3.722. Now you see here the after decimal how many digits are there. Now count the digits in the addition and subtraction. You count that after decimal how many digits? 3. Here how many digits? 2. Here which one is least precise? This one compared to this? Smaller, which is a smaller person? This one. After decimal 2 places, 3 places. So in the result I will keep which one? Up to second 2. So I will take the up to 2. So this should be dropped. This 2 should be dropped. So now by rounding off, I will write this as by rounding off 2 is dropped. It is less than. So I will write 3.72 as it is. 3.72. If suppose it is you got this as 7. So suppose here you will get 7. So the result will be 3.72. We will drop this one up to 2. So this is greater than 5. So I will write this as 7.3 by rounding up. This is the addition or subtraction. Clear? Then we will go for the multiplication and division. Okay, so now come to the multiplication and division operation. So let me write the rule. The same rule for multiplication and division. Both are having same rule. Follow the same rule. When you are doing the multiplication operation or division operation, both follow the same rule. Like your addition and subtraction follow the same rule. Here also the same rule. Let me write the rule. We will retain the significant figures. We will retain the significant figures. We will retain the significant figures in the final result. In the final result of multiplication or division. Multiplication or division equal to the least number of significant figure. Equal to the least number of significant figure. Least number of significant figures. Here you have to calculate the significant figures. Least number of significant figures in any of the numbers. Got it? We will retain the significant figures. The significant figures will retain in the final result of multiplication and division equal to the least number of significant figures in any of the numbers. Means when we are doing the multiplication or division, then calculate the significant figure in each of these numbers, and in the result we will keep the least number of significant figures in the operations where we are use the numbers. In the result we should keep least significant figure which is in the operation of the numbers. Means we are operating the things like that. So let us take an example that 4 point example is that suppose I will take a 4.192 multiplied with, take an example is 4.192 multiplied with 2.02. Now multiply. Use your calculator and you multiply. So you will get the result as I have the value. Okay, I have a calculator, so I can use the calculator here. So I will use that calculator and I got the result as 8.4678, 8.4678, 8.46784, 8.46784. I got the result by using my calculator. Okay, let me correct. If I wrong, let me correct. So here it is 4.192 into 2.02. So this is 8.46784. That is my result. But now you see here, what is the significant figure in the quantities you are using in the operation? In the multiplication, here the significant figure is, how much is the significant figure? 1, 2, 3, 4, all the non-zero, 4. Here the 0 lies between 2 non-zero, here it is 3. So in the result, we will retain what significant figure? We will retain the significant figure how much? 3. 3 significant figure means I will take, from here you count, this is the first significant figure, you cannot drop this one, this is the second one, this is the third one. So I have to drop this from here, I have to drop this one, means I have to take this significant figure up to this, then I have to drop this one. So this one is dropped, now we go for rounding up, means I will keep up to what? 3. So 3 means I will drop this one, means this one is dropped, 7 is dropped. According to round off rule, the digit what is dropped is greater than 5. So the result I will write this as 8.4 raised by 1. So this is the result, 8.47. Okay. So this is the multiplication rule. Now you can go for one example for division. So what I will do for a division case. Now you take a division, like suppose I got a result here 7500 divided by 20.83, 20.83, and by that the result is 7500 by 20.83. You use your calculator and you will get the result as a 360 point by 360.0576. I got this by using my calculator. Okay, I got this result by using my calculator, and you can do that, operation in your using your calculator. So I got this result. So now come to the rule is what? Here you calculate the significant figure. In the operation I am using this one and it has a significant figure. Let me write here 2, because the zeros followed by the non-zero digits. The zeros followed by the non-zero digits to the right, they are not significant. So these zeros are not significant. So 7 is significant, 5 is significant. So it is 2. Here it is a 0 lies between 2 non-zero digits. That is significant, because the point is that all the non-zero digits are significant, but the game is for to know whether 0 is significant or not. That's why you are used that 5 rules. So the rules of counting the significant figure, when you go to the significant figure, all the non-zero digits are significant, but the 0 is whether significant or not, that is for different. So here the 0 is lies between 2 non-zero. So this is significant. So how much here? This is 4. So here it is 2, here it is 4. But in the result you see up to what significant figure I got? These zeros are significant. They are lies between 2 non-zero digits. So this is decimal. So 1, 2, 3, 4, 5, 6, 7. In the result I got 7. But the rules tells me that operation of the operation in algebraic operations, by using that significant figure rule, it says that you should retain up to what? 2 places. Means so 2 significant figure, not 2 places, it is 2 significant figure. So to keep to 2 significant figure, as you know, 3 is significant, 6 is significant. You will try from what? From the left you go for, don't come from right, come from left. So if I retain 3 and 6, then you can write 36, but that is wrong. Now you compare that. This is a general obvious concept that a result has 360 point something, but I got that by rounding up, I got 36. Now count the difference. This much of difference is not allowed. You are rounding up means if you are rounding, if I take 50 rupees from you, so I have to return 49 or 45 or 55 rupees. If I return 10 rupees, then it is not allowed. So accordingly, 360 by rounding up, you cannot take this as 36. So you have to take the 2 places means, but the rule should be followed. So 2 places means I can put 0 here. there is no problem. Because this 0 is not significant, but the result is obviously same. So I can write this is equal to, the result is 360 by using the significant figures in algebraic operations. So the result will be here 360. So as it is, how many significant figure here? 2, and there is no change in the, there is no much change in the value. So you can retain this value. So we will write the answer as 360. Okay, students. So we go for, in this video we have discussed about the significant figure, rounding off, and the significant figures in algebraic operations. Go through these videos and you can get a clear idea about the topic. Thank you.